great.
Okay. So, good afternoon, everyone. It's a great pleasure to have Professor Lu. He is a leading expert in the field of scientific machine learning and PIN here with us today. Professor Lu is an assistant professor at Yale University. Previously, he was an assistant professor at University of Pennsylvania and a mathematics tutor at MIT. He obtained his PhD degree in applied mathematics at Brown University. His current research interest lies in scientific machine learning, including theory, algorithms, software, and its application to engineering, physical, and biological problems. His broad research interests focus on multi-scale modeling and high-performance computing for physical and biological systems. He received numerous awards, such as US DOE Early Career Award. He is also an action editor of Journal of Machine Learning. Welcome, Professor Lu. It's a great pleasure. Now the floor is yours.
Yeah, thank you for the introduction. So today I will share some of recent works on physics-informed deep learning by considering not only data set, but also physics together for learning functions and operators. So let me start with a very simple textbook version of deep learning. So in deep learning, essentially what we try to do is approximate some unknown function, such as UX, mapping from one RD to R. Then we consider we have a data set, a T with finite many data pairs, X and Y pairs. Then we can design a neural network with many different hidden layers. Then each hidden layer is denoted by the Z here. And in each hidden layer, we have the trainable parameters, weights and biases, W and B. Then we design this network. Also in between hidden layers, we have the activation function, which is nonlinear. Then we have a loss function to measure the difference between network prediction and my ground truth in the data set. Then by minimizing this loss function or train the network, we can obtain an approximate version of the underlying ground truth function UX by using the network. So this is a very straightforward and standard deep learning framework. So in order to train a deep learning, especially large-scale networks, for example, nowadays foundation models, it indeed requires a lot of big data set, or big data. So this is a standard machine learning framework. We do not consider any physics, but only from data set. Or in another stream, probably many of you are pretty familiar with many different techniques in scientific computing, such as find difference, find element, molecular dynamics in the small scale or multi-scale method, multi-scale modeling. So in these standard scientific machine learning methods, usually what we do consider is we have the underlying physics. We have the physical equations in terms of PDEs or ODEs. Then in order to solve this system, the only data set we need is the initial condition of the system and also boundary condition of the system. So it's a really small data set. So these are two extreme cases for scientific computing and learning. But nowadays we consider in many engineering problems, we do have some physics, but also we have some data. Either could be non-perfect. So physics-informed machine learning or scientific machine learning, what we try to do is develop new machine learning techniques that can handle the case in the middle. So data set we consider could be not perfect. It could be dinky, dirty, dynamic, or deceptive. And we also have some physics, but physics may or may not be perfect. But here the physics could be arbitrary or any scientific domain knowledge, could be physical principles such as the underlying partial differential equations, or it could be simply some physical constraints, mass conservation, energy conservation, or it could be some symmetries principles in the physics, or even it could be some computational simulations. So by combining both the data set and the physics together and developing different scientific machine learning methods. So we aim to have a method can be more accurate and efficient. And more importantly, in this talk, I will emphasize a lot on the robustness of the method to be generalizable and also reliable. So this is overall idea of physics-informed machine learning and what we try to do. Let me start with a very specific method in this physics-informed machine learning or scientific machine learning. This method is called physics-informed neural network. We have worked on physics-informed neural network for many years, go back to 2017 or 2018. And now physics-informed networks or PINNS has been a very popular and important method in this research area. So this method has many different advantages. I will show you by using this simple example of diffusion equation. Let's say we have a system simply described by this 1D diffusion equation, du dt is equal to lambda d squared u dx squared. Assuming we have a data set for training u, that's straightforward. But also we consider how can we train a network for the output of u also using the physics, which is the equation I showed here. So the network here, this is standard network. The input is x coordinate and the t coordinate. The output is the solution, the u hat, as an approximation of the underlying ground truth u. Now, let's see how can we construct a network or construct a loss function in terms of this the equation here. So the idea actually is straightforward. We can compute the difference or the error of the loss function, so du dt minus, which is the left-hand side of the PDE, and minus the right-hand side of the PDE, the lambda d squared u dx squared. So we can compute this at different location of x and t, and for the corresponding output of network u. So by when we train the network starting from a random initialization, this term is not zero. Then we can add this term into my loss function and minimize the loss function, this loss function together with other losses, for example, data loss, or if you have extra boundary condition loss or initial condition loss, then this is the overall loss function to be trained. So essentially, when we do in the PINNS, so we train the network, try to minimize the loss function in terms of our physics. Here, the physics is the PDEs. So one unique advantage of the PINNS compared to traditional scientific computing methods, such as the difference of an element, is that in PINNS, we can compute the partial derivatives, for example, du dt, without any mesh by using back propagation. So, so this is also called automatic differentiation, or AD. So the derivatives can be computed without any discretization error. And also it does not require mesh. So it's mesh-free and no discretization error. So this is the first advantage. And also in this framework, you can see we can train a network by integrating both the physics information and also data information. So this is the key idea of PINNS. And now let's show you one specific application we did recently to show the advantage of PINN on real applications. So this is a biological problem. So here I show you many different biological tissues, from the heart tissue, aortic valve tissue, and the brain tissue, and many other different tissues. Then all these tissues are very important for biology in many biological applications because we can infer many different properties of underlying diseases or the organs from the tissue properties. For example, the tissue micromechanical properties can be related to the function or dysfunction of heart valves, can be used as a diagnostic indicator of the diseases, for example, cancers. So what we try to do in this project is, when we given this unknown brain tissue, so this is one image from real experiments of the brain tissue, and this is an image from the also experiment from the valve tissue. So we try to infer the structure of the tissue structure, but in terms of the Young's modulus E here. So we try to know this mechanical property E of the tissue. Then we can do some experiment. So here in this experiment, we can do the stretch of the tissue of this small patch on the 4 boundaries. Then after stretch, we can measure the string fields, so epsilon here, in different directions. Then the goal is we try to infer the elastic modulus E from the string field epsilon. But here we notice that the modulus E to be inferred is not a constant. It's a space-dependent elastic modulus. So it's basically a heterogeneous material. And in this case, we do not have any support data. The only data set we have is for this specific setting, we have the measurement of the 3 images, the epsilon. So we cannot train a network in the standard data-driven version. Then we apply PINNS for this problem. So it's quite similar to what we have discussed earlier for the diffusion equation. But here the difference is the problem setting is more complicated and we have more equations. So here I'll show you all the equations we will embed into the network for training. Still, the network input is the coordinate x and y, and output, this is many different outputs. So we have all the string fields as our network output, and also we have the elastic modulus as our network outputs. So we have many different outputs, and then we have many different loss functions in terms of all these equations here, and we have one data measurement, which is the string field. Then we train all the loss together, PD loss, data loss, and also other constitutive illusion loss. Then after the training, we have the prediction of the unknown elastic modulus field E. So this is one prediction. So on the top, we show for this brain tissue and tricuspid valve tissue for the ground truth and our network prediction. And here I also show the point-wise error between the ground truth and our prediction. So overall, the prediction is pretty accurate. You can compare the 2 images. And overall, the error is 1% or 2%. So this is the real application on real experiments data to show the advantage of PINNS when applied to this complex problem. So this is just a demonstration. So, but in PINNS, although this framework is simple, but actually there are a lot of things can be improved in terms of different components of this framework. First, as I mentioned earlier, in order to train this network, for example, we need to select some locations of x and y in order to compute the loss function of the PDE. Then what's the optimal way to select the spatial temporal points, or these points are also called residue points? Actually, it's a question, and it would affect the accuracy a lot. So here, let me show you one way we proposed for the selection of the location of the training points. So there are many different standard ways to select these points. For example, I showed you here different pictures. So the most simple way is we draw a grid, as what we do in find difference of element. So we draw equi-space grid, and these grid points are used for training. Or as I mentioned earlier, the PIN method is mesh-free. We don't have to use the equi-space grid. We can do random sampling. So here I draw this random sampling on this 2D space. So in addition to this this standard random, we can also do many different other random sampling. For example, LHS, which is random half-cube sampling. Or if you are familiar with different version of so-called a Hamilton sequence or Hamilton sequence or Sobol sequence. These sequences, if you draw the points in 2D, they are similar to random, but this is not a random sampling. They have a deterministic way to sampling, but it looks like random. So we can apply all these different random sampling methods for PIN training, and they have different performance. And I will show you later in a figure. So indeed, the different sampling have different performance. The grid sampling actually does not work well in many different cases. But let's go to another more interesting sampling is that instead of we do this deterministic sampling, we can do sampling in more adaptive version. So here I show you a 12 problem of Burger's equation, actually with a small viscosity. So this is a solution of the Burger's equation. And in this solution, you can see we have a sharp, the solution is pretty sharp when x equals around 0. Actually, this is a sharp. If you assume we do the random sampling, for example, as shown in the black dots here, so it's hard to capture the shock here because we do not have enough training points. So usually when we do fine difference or fine element, we would apply a mesh refinement and or draw a denser mesh around this location. We can apply this idea also to PINNS. So we can start with a random sampling location using the as shown in the black dots here. Then we do the training for some iterations. Then we can check whether location with large PD residue. Then we add more training points in the location with large error, as shown by the green cross here. Then by using this adaptive training, we can reduce number of training points, for example, from 10,000 to a few thousand to achieve the same accuracy. So this is one way to do the adaptive sampling, and you can see this is sort of a greedy method. We add more points in the location with the largest error. Or instead of do this method, the sampling or adaptive sampling in the greedy version, we can do this adaptive sampling in a more balanced way. So for example, if this is our PD error or PD residue, so we have large error in the center and a small error on the boundary. So this is just a demo example. It's not the real case. Then we can sample more points according to this equation I show you here. So basically, for each location, we can measure what's current error of the PDE at this location, which is epsilon x. Then we can sample more points on the location with large error, but also we try to balance the points with small error. So our final sampling probability density function is equation according to both the error of the PD and also we plus a constant here. So if this constant is large, then it will lead to more uniform sampling. If for small constant and large value of k as exponent here, it will more toward to the non-uniform sampling and focus on large PD error. So you can see in this different the power here, by tuning this coefficient k and c, we can have more points concentrated on large error, or we can have more points more like uniform. So this will be balance. By tuning this k and c, we can have a more balanced sampling at different locations. Then what we can do is during the training, we can train our network for 13 iterations. Then we adjust our sampling points, training for another, let's say, a 5,000 iteration. Then we change our sampling again. Basically, we do this adaptively, or we repeatedly add more and more points according to this PX. So this method we call it as residual-based adaptive refinement, but with this specific probability density function, we call IARD. So here I show you 4 different examples about the accuracy and performance for different methods. So for simple equations, for example, diffusion equation I showed you earlier. So even the very standard grid sampling, we can achieve a small error, that's 0.6%. But for more difficult problem, for example, Burger equation or Allen-Kane equation, or wave equation with high speed wave, then the simple sampling method would not work well. For example, grid sampling or standard random or LHS, you can see for Allen-Kane equation, it will have large error. Then the Hemsley, Sobel, and Helton, they can do well for these equations. But for the RIR equation or RIR method, this adaptive sampling, we can achieve even more better accuracy, even more for more complex equations. So as an overall suggestion, so adaptive sampling usually works much better than deterministic or fixed sampling strategy. And even for fixed sampling, the grid is always not a good idea. I see a question here, maybe I can answer right now. So for random sampling, deterministic can show correlation between successive samples. I'm not sure what's the specific meaning of this question. Yeah, maybe I will go back to this question later. Okay, so this is one specific angle to improve the performance of the PINNS. But actually, in PINNS, there are many different ways can improve its accuracy or efficiency. So in addition to this adaptive sampling, we have developed many different extensions of PINNS. For example, how can we modify the network architecture? We can also modify the loss function. We can also modify the training strategy. Then we can apply all these different versions of PINNS for solving different applications. But this is the first half of my talk today. But in PINNS, so still we have one limitation is each time when we train a single PIN network, we can only solve a single PDE. For example, as showed for the biological problem. For each time when we have new material, I have to retrain my network from scratch, which could take from minutes or 2 hours, depends on the specific problem complex. So in the next stage, we try to solve a class of PDEs simultaneously. So this is called operator learning. So let me show you a very specific example here. So here, this operator learning, what I mean is a function or a mapping from function to another function. For example, derivative operator. So maps from a function xt to its derivative x prime t. Or we consider integral operator from xt to integral of x with respect to a kernel k. But still, I will consider PDEs. Then in PDE setting, we will learn a mapping definitely by neural network to predict the PDE solution directly from the boundary condition, initial condition, or forcing terms in my PDE. So this is what we try to do in this operator learning. So there are many different ways to do it by using neural networks. So here, we introduce a method called DeepNet. And in DeepNet, so first we consider we have an input function u, as u is function. So we cannot directly input this function into my network, right? Because the function is continuous and it's infinite dimension. Then in the first step, we need a finite dimension approximation to represent my function u. There are different ways to do it, and a simple way is we can have a dense points x1, x2 to xm in the domain of u. Then this vector ux1, ux2 until uxm, they are the pointwise function value at these locations can be used to approximate or represent my input function u. Then this can go to my network. Then for the network output, still is a function. Oh, sorry, I forgot to mention a few notations here. So let's say the operator I try to learn is denoted by this G. So G is the operator. For example, the mapping from the boundary condition to the PDE solution. And U is the input, for example, could be the boundary condition or initial condition. The GU is my PDE solution. But as GU is a PDE solution is a function, so we cannot predict the function directly. Then in order to predict this function at arbitrary location, we have another network input denoted by the y here. So y is a point in the domain of the GU. Now the network output becomes the GUY. So GUY is the PDE solution evaluated at this specific location y. Then in this way, we can predict the PDE solution at arbitrary location y, not restrict to any mesh. So it's mesh free. And also, when we train this network, in many cases, we need to compute the PDE loss, which means we need to compute the derivatives of the GU with respect to y, right? Because GU is the PDE solution, y is its coordinate. Then by using the same idea as PINNS, then we can compute the derivative or gradient of GU for y by using automatic differentiation. Again, this no error for computing these derivatives. And specifically, if you look at the network architecture, so we have 2 inputs and 1 output. Then we decompose the entire network into 2 parts. On the top, we have branch net. On the bottom, we have trunk net. So the branch net takes the yield function as input and outputs a hidden vector b. And the trunk net takes y as input and outputs another hidden vector t. Then the final, the output GUY is computed as a dot product between b and t. Or as shown in the equation here, is summation of bk/tk. The k is the index. So this is a simple way to construct the network, inspired by the following idea. So because GUY essentially is a function of y, right, is a PDE solution. And for different cases, we have different solution. Then the TK here can be viewed as a basis function of y. So essentially the basis function in the space of the PDE solution. Then for specific input, essentially we will have different coefficients for the basis function. Then the branch net will predict the coefficients, and the trunk net is a way we construct the basis function. So basically we use this specific network to learn what's the optimal basis function for the specific PDE. So here is just a simple toy problem to test the performance of dipole net. So a Darcy problem, but here the complex, actually we have a complex geometry. So it's a triangle with a notch. But because the dipole net is mesh-free, it can be applied to this problem directly. So in this problem, what we try to do is to predict the PDE solution for different boundary conditions. Then we can do the training using data-driven training, or we can use the training using the PDE loss, or we can do the hybrid training. So, and after training, this is one specific test case. On the left, we have the ground truth, and on the right, we have the dipole net prediction. So it's pretty accurate, basically 1 or 2% error. So now let's go to another more realistic example. So this is an application called 4-wave inversion in geoscience. And in this problem, we try to infer the subsurface structure, which is called velocity map C, from the seismic data. So let me introduce the background a bit more. So let's assume we try to know this structure for my subsurface. And what we do is we have a car here, and this car will generate a wave. So you can see we have a wave showing here, and this wave propagates in this structure. Then we have many sensors on the top of this surface, showing the orange dots here. Then this sensors would receive the signals of the wave. So for example, if for this specific 2D structure, let's say our car is in this location C. So we have the C, we have the car here, generating the signals. Then on the top, we have many different sensors. Actually, here in this example, we have 70 sensors. And each sensor receives a time series signal. Then we put all these signals into a single matrix. So each column is a signal received by one sensor. Then we put all these sensors together, so it becomes a matrix. Then we can put the car in a different location, for example, location A, location B, or C, D, E. Then for each different location of the car, we have different signals received by the sensors or receivers. Now what we try to do is predict this velocity map, the 2D field, from the seismic data, basically these 5 different images. So this is the inverse problem. Or if you look at this underlying mathematics, this is the PDE. So the pressure is the signals, and S is the source generated by the car. So basically, we have different sources for this PDE, and then we have different solution of the pressure. However, we only have the measurement of the P, not for the full space of XZT. We only have the measurement on some specific X, and when Z equals 0. And C is the field we try to infer. C is the velocity map. And here is the one signal S, the origin line. could be clean or could be have noisy. So we apply DeepNet for this problem. So input is all the 5 images of the Sesame data, and output would be our velocity map C. But here we have a modified version of the standard DeepNet. So in the standard DeepNet, so if I go back to here, we construct output from 2 branches or two sub-networks by using the simple dot product. But for this complex problem, we replace the dot product with more complicated network architecture. So we put a few hidden layers net here, a hidden layer here, instead of using a simple dot product. And in each hidden layer, we apply the architecture from the either the UNet. So the UNet is standard serial network architecture, or free network. Or it could be a fully connected network. It's either fine. So this network architecture, still we have branch net and trunk net, but just more complicated network for reconstruction. So the prediction is pretty accurate, but here I do not focus on too much on the accuracy. I try to show the robustness of the trained network, also called auto distribution testing. So in the training, we have the clean data set, but let's say in the testing, we add extra noise in the network input. So for the training, there's no noise in the network data set. So, but assuming we have the noise for the network input during testing, then intuitively, because we have never seen this noise in the training, then for testing, we have large error. So this is true for many different network architectures. So in addition to the network we developed called the free DeepNet, we also compared with other networks, for example, so-called inversion net or velocity GAN. In these two networks, when adding the noise into the input, then the prediction would be really bad. But we see for the free DeepNet we developed, we can still have a good accuracy compared to ground truth. So this is one testing example of the ground truth. We can still have good accuracy. And on the right, we have another testing example, but different underlying structure of the velocity map C. So this is really interesting. So it shows the robustness of the trained network. Or we can show another robustness is, so let's say in the testing stage, there are so many receivers or sensors that somehow failed and don't work. And in the data set, which means in many columns in our input, there's no signal for those columns, or the signal is purely just 0. So we have this really bad input. Still, intuitively, we cannot guarantee a meaningful prediction because our input is totally so it's totally destroyed by this missing data. Again, by looking at other networks people developed in this field called inversion net or velocity GAN, their accuracy is bad compared to ground truth. So this is one testing case. So you can see, although we have some structure can be observed, but the value is off. But for the our developed free DeepNet, we can still have a relatively good accuracy. So even if for this missing data input. So this is a really interesting phenomenon we observed in our experiments. However, we cannot explain this in theory because by the standard machine learning theory, the network cannot be guaranteed to have good prediction for auto distribution data or for data set not you have never seen in the training stage. So this is one interesting direction we are currently continuing to explore. But still, training all these networks requires really a lot of computation. And now we try to, how can we try to reduce the cost, both in training time and also memory. So one idea actually is straightforward. People have applied a lot in standard machine learning applications, for example, image classification. It's called a low precision, for example, float 16 applied in the network architecture. So in the standard machine learning, we use float 32, or even in scientific computing, we use double precision, float 64. But we can apply float 16 in the network training. However, by applying this idea directly into the regression problem, for example, even if for this simple function regression, fx equal to x sine 5x, we found that by using half precision or this low precision, our accuracy would be a decrease a lot. For example, when we train this network using float 32, we can have 1% error. But if we use float 16, our error is 10% almost. So the reason is we can check this in terms of the training, look at the loss, training loss, and also the gradients, the value of the gradients. So we found that for the regression problem, because we indeed, in many cases, require a high accurate gradient value to update the network. By using the float 16, the gradient cannot be, it has large error and cannot make sure our network will converge to a local minimum. This even be a more important issue for PINNS. So for PINNS, if we apply float 32, then this is the loss landscape we plot into the 2D dimension space. So it's smooth and network can be trained. But when we apply the float 16, even if at iteration 0, you can see the loss landscape is really bad. And even in many cases, this is NaN, so not a number. Then this is one idea to extend this by using mixed precision, which means for the forward propagation, we apply the float 16. Then for back propagation, we first apply float 16, but when we apply this specific optimizer like Adam, we use float 32. So this is a mixed way to use different precisions. But in addition to this, to make this mixed precision working well for regression and PIN problems, there are many other technical details we have to apply. So we have many details, I think around 5 different technical details we showed in the paper. But once we apply this technique for PINNS, for this network stop problem in this channel, then we can see we can still maintain relatively basically the same accuracy, but reducing the training time by 50% and also reducing the GPU memory by 50%. All this is a physics-informed deep net problem, a diffusion reflection equation. Still, we can maintain the same accuracy as float 32 by using mixed precision, but reducing the training time by 50% and also reducing memory by 15%. So this is already implemented in DPSDE in our software. Basically, by using this, we can have faster training, less memory for free. So we have also other techniques to improve the deep net. But in the last topic here, I will show you an interesting direction we currently exploring. Is called interpolation. So as we know, all the machine learning methods, including deep nets, can only be applied to interpolation. So although in this example here, I showed you some example of interpolation. However, this interpolation, I would say, is still simple interpolation. So for example, because compared to our trained data set, although we have some missing value here, we have large noise here, but more or less, there are still some similarity. But now let's go to a real interpolation, a totally different data set for training and testing. We start from a more well-defined setting. Let's say we try to learn this operator G, maybe from the space V to U. And we sample all the functions for training and testing from a space called the Gaussian random field. And the Gaussian random field, we apply the kernel called RBF kernel. And in this kernel, we have a parameter called L can be tuned or can be selected. So for example, if we select a large value of L, then all the functions we random sample in this space are quite smooth or almost flat, like this. And if we use a small value of L, let's say L equal to 0.1, then the functions become more oscillated and complex. Then let's say if I train the network using the functions in one space, let's say in this L equal to 1.0. But if we try to test for the functions in the L equal to 0.1 space, then there's no way to have good accuracy. Because the training and testing, they are quite different. So let me show you one specific example, look at about the accuracy. So on the left, we have ODE example, DODX equal to U. DODX equal to V. And we learn the solution to learn the mapping from different U to the solution, from different V to the solution of U. So we train and testing the deep net using different spaces. So on the x-axis here is the correlation length for training, basically the correlation length of the training space, and the y-axis is the correlation length of the testing spaces. Then in the diagonal line, so training and testing, they are in the same space. So this is the interpolation. So we have good error for sure. Then on the top, a triangle here. So in the here, the correlation length for training is smaller than the correlation length for testing for this part. But still, although we have different space for training and testing, but we have still good accuracy as shown in the plot. So the color is the error, the testing error. So we call this as extrapolation minus. But if you look at a lower triangle, in this part, we have correlation for training is larger than correlation for testing. Then indeed, we have a large error. So we call this extrapolation plus. So the same phenomenon can be observed in many different cases, for example, diffusion reaction equation. So we try to address this issue of extrapolation. How can we still have a good accuracy even for extrapolation? But before that, we propose a way to quantify the complexity of extrapolation. So assuming we have two spaces, F1 and F2, from Gaussian random fields, then we can apply a metric called the W2 metric, showing the equation here to measure the similarity or the distance between two spaces. But here we show this distance, W distance, can be used to quantify the complexity of extrapolation. For example, for the ODE example and diffusion equation example. So in experiments, we observe a strong correlation between the extrapolation area and W2 distance in the log space. So by using this, so we propose an entire framework for extrapolation. So let's say we have a pre-trained deep net on an existing data set. Now we have a new input, basically a new space, for prediction. Let's say a function called V. Then we can first apply the pre-trained deep net for prediction. Let's say our prediction is U tilde. Then by using this W2 metric, we can first quantify what's the level of complexity of extrapolation. Do we have a lot of extrapolation or just a small extrapolation? We can set a threshold of epsilon. So if it's interpolation or a small level of extrapolation, then we roughly are confident, okay, our prediction U tilde is accurate. Then we can return U tilde directly. If extrapolation level is large, then the U tilde will have a large error. So we have to propose a new method to improve the accuracy of U tilde or correct U tilde. We have many different versions of specific method, but in general, we need to require extra information, right? We cannot have good prediction just without any additional information. The additional information we consider could be some physics, for example, governing equations. Could be we have a new data set for a new case or new space, but definitely the new data set we assume would be sparse. Then given this new information, we can do the fine tuning of the pre-trained deep net. Right? Nowadays, fine tuning is really an important approaches or method. For example, people trained ChatGPT or many other foundation models using existing data set. Now, when you try to apply this foundation model for a new case, we do fine tuning. It's the same thing here. We have a pre-trained deep net. You can view this as a foundation model. Then for a new case, we do fine tuning. But this fine tuning can be based on physics fine tuning or could be based on data. And in our paper, we have proposed a specific different methods for fine-tuning. And another idea is called multi-fidelity learning. So I will not discuss in this talk today. But let's look at the example. So this is a data set of many different pairs of the daily surface at temperature Tx and pressure Px, as shown in the plot here. So this is the temperature and the pressure on the date of January 1st, 2021. And we have data set from 1950 to 2021. So for 70 years. Then we try to train network, predict the pressure from the temperature. However, we only train my network using the dataset in the first 5 years. Then we test for later years. And in the plot here, you can see for later years, we have larger and larger error. Well, this is because we have the global climate change. The correlation between the temperature and pressure are changing during time. So essentially, we have extrapolation for later years. Now, how can we improve this? We assume we have extra data set. So here we assume we have 100 weather stations, and the black dots here are in this global Earth surface. Definitely, compared to the entire surface, is sparse. So it's a sparse data set. But by using this sparse data set, we do fine tuning, then we can improve the error of the prediction. So this is the improved error which is 0.7%. So in addition to a few deep nets I discussed today, we have also many other different versions of deep nets. For example, multiple input deep net, multi-fidelity deep net, and also we have recent work on one-shot learning. We have also applied these networks for different applications and have some theoretical analysis. And at the end, I would like to introduce the software for all the research we have done in this talk and beyond. So DeepSD is the software we developed for scientific machine learning and physics-informed learning. So this software has been used by many universities and initial labs, and also even companies in the industry for many different papers. And it's open source in GitHub. And there are, in addition to our group, there are many other people around the world keep adding more and more features into the software. For example, Kwandai, he has added a really amazing feature called ZCI zero-shot method for computing derivatives efficiently, can speed up the derivative computing by even order of magnitude for both computation cost and also the memory as consumption. So yeah, feel free to use this software or adding more features. With this, I would like to finish my talk, and thank you all for attention.
Thank you, Professor Lu. This is a very nice talk. So if we have any questions from the attendees.
Yeah, there's one question in the chat, maybe.
Yes, this is about the random sampling question. So yes, I mentioned earlier. So although here I so-called random sampling, but actually it's indeterministic sampling. So which means we generate these random locations at the beginning of the training, then fix it. So it's deterministic. So compared to this version of sampling, so this is non-deterministic, which is adaptive, or we call adaptive sampling. So we keep modifying the training points during the training. But for the second half of the question, I do not really get it to show correlation between successive samples.
Yes, it's kind of like, say, it's kind of a, a Markov chain, right? Like this adaptive is very much like, I think it's
yes,
like a Bayesian optimization, like
yes, exactly. You can view this as a Markov chain. So basically, we have a chain of different samplings for the training of PINNS.
Yeah.
So
I have a question. So it's kind of practical. So we apply physics informed machine learning, like
Yes.
in DeepNet and also like neural operators. What we found is like in many cases when you put in the physics constraints, the accuracy drops. And we wanted to, so it could be understand if you just feed the data, it could give you better accuracy on the testing set, right? But adding the physics are supposed to give you better generalizability. But this is just, what we thought. But in practice, we find, sometimes you get the best result without adding physics.
I see. So in general, in all applications, usually in general, I think is adding, as we discussed, adding physics would improve the accuracy. But I agree, in some cases, it could be hurt. There could be due to a few reasons. So one thing in some applications we found is, in some cases, the when we try to generate data set, we apply some method, find difference, find element, or some other approaches. But when we apply the physics, we have the equations. And sometimes this is inconsistency between the data set and the PDE equation. So, and this would hurt the performance. So basically, they are not exactly consistent between these two losses. So this is one thing we noticed in some of our examples. I'm not sure whether this is true for your part.
So is there any like, especially for instance, for some simpler equations where the data is kind of abundant, right? That's the case where I'm wondering, is any kind of practical measures, like for instance, like adaptive weights that could be
Yes. Yeah, I think this is a good point. So basically, when the training, when we have two losses, so for example, in a recent application, we applied DeepNet or physics for DeepNet to a problem in the manifold. We found that in order to make or improve accuracy by adding physics, we have to tune the weight of the PDE loss. So tune the two ways. Currently, we didn't have a good way to automatically tuning. Actually, I know there's probably a couple of papers to do the automatic tuning, but we still do this by manual tuning. Yes, so it's important to tune the weight. Otherwise, sometimes it could hurt performance.
Yeah, thank you.
So I have a very trivial question, probably. So, I mean, as far as I understand that you feed training data set, which includes initial condition, boundary condition, and then PDA data, right? So the amount of sample in the initial condition and boundary condition may be much less than the PDE data, right? So how do you feed proportionate amount of data, or you give more PDE data, less initial, less boundary?
So for example, in this case, we try to predict the PDE solution actually here for different boundary condition. So what we need is we need the same number of pairs. For example, for each boundary condition, we need a corresponding solution. So this is the same. But for the boundary condition, for example, this is a specific curve or boundary condition. We may have, let's say, 100 points in this curve for the boundary condition. But for the PD solution, which is the 2D in the triangle, we may have 1,000 points. These two can be different, and DeepNet can handle this directly.
Okay. And what about in PIN situation? What do you do?
Oh, in PIN situation, so yes. So in this talk, I mainly focus on the PDE, the point for PDE loss. But you are right. So usually we have, for example, we have boundary condition loss, PDE loss. In general, because PDE, for example, in 2D is square, so we still use some heuristics from fine difference. For example, if my domain is 2D square, we have x, y. Then if I sample roughly 100 points on the boundary, then if we consider a grid, it's uniform mesh, then we need 10,000 points inside.
Yeah.
We can use this guideline to select number of training points. But actually, for example, in 2D, we can use fewer points than 10,000 for PIN for training. So there's no need to use 10,000. But this rough number can be used as a guideline, as an initial starting point.
Okay, thank you. So we don't have any questions.
Right on time.
Yeah. Yes, so shall we conclude this talk?
Yeah.
If no talk, yeah.
Right.
Thank you, Professor Lu.
Thank you.
Thank you.
Thank you.
Yeah. Bye.
I'll talk to you later.
Sure. Talk to you. Bye.
Bye-bye.
Bye.